Well, welcome, Vest Scholars, to your final project. I'm just going to briefly go over your final project, at least some of the basic content behind it, and then it's your job to take it from there. Um, I'm going to do by way of example here. One of the concepts that's really important to understand with regard to Earth system science, and especially as we see things today, is that of course all these spheres that you've been studying have interactions and a something that happens in one will have effect on the others and so forth. And sometimes it's a cascading effect. Other times it's just a return to a dynamic equilibrium. Sometimes it throws things off completely. But you've seen a lot of that happen throughout this course. One of the big things that is more of a secondary or even tertiary effect of human activity today is biodiversity loss. We'll return back to this at the end of this presentation, but just to start off to say that biodiversity loss is a major problem today. And, this is an opinion piece that came out in the New York Times a little while ago, but asking the question if we're in the midst of a sixth mass extinction. This is one of the pieces of evidence that scientists use to discuss this concept of the Anthropocene, which is potentially a new geologic epoch. It's not officially an epoch right now, but a lot of scientists are discussing this, and one of the aspects of that is biodiversity loss. And it's not that humans are necessarily going out and hunting down all these animals, or using them for food or whatever the case is, but a lot of this is secondary. So if you destroy habitat through deforestation, forest fragmentation, if you decrease the quality of freshwater systems and marine water systems. That, of course, have secondary and tertiary effects on extinctions. If you take a keystone species out of an ecosystem, that has an effect on other species. So maybe, if you're protecting through conservation efforts a particular large mammal, what about the rest of the species in that ecosystem? Are you protecting those as well, or just protecting the lions, for instance, or the white-tailed deer here in the east? There's a lot of interesting questions here, and humans we're not very good at managing these things, really, especially when it comes to planning for the future. But if you look at this, if you pause for a while and just study this image, this is one representation of it, of the current biodiversity loss reality. The You're looking at big groups here: birds, mammals, and amphibians. Amphibians are really going through some major biodiversity loss issues, but large mammals are as well. Of the ones assessed by the Union for Conservation of Nature, which is they maintain what's called a red list of threatened and endangered um, um, species. You can see percentages of the species we know of, and these are the species we've identified and have seen in nature. Um, these aren't even including all of it. There's a huge bunch of unknown species, and not so much large mammals in this case, because typically we know where a lot of large mammals are, but and then of course already gone organisms. Um, but these red areas are really the part to focus on, and these losses are significant. And really, what it comes down to with regard to extinction is extinction rates. So, there are five big mass extinctions that have occurred in the Earth's past. Five that are agreed upon. There's the late Ordovician, and then there's the Devonian, there's the Permian, and then there's the Triassic, and of course the Cretaceous Paleogene extinction, or sometimes called the KT, or Cretaceous Tertiary extinction. These are the big five. This was the one that knocked out the dinos. This little Triassic one is the small one, probably the smallest of the five. Although here, in terms of extinction rate and loss of families, it seems to edge out the Devonian. But the Devonian was a long extinction interval with several pulses to it. Largely, we think due to eutrophication of waters. There are a lot of shallow marine environments and plants were evolving at a very rapid rate at this time. And of course, as they evolve, they die, and then they get into you have nutrient overloading in these shallow marine environments, leading to the production of algae and so forth, and then eventually black shales through that during that time. So big extinctions, but probably over the course of actually 30 million years. Whereas this extinction was pretty instantaneous, and as were the other ones. The Ordovician extinction was, we think, the main other one related directly to climatic changes. I mean, they all have it. They all have an element of that, but the Ordovician one in particular. Um, but there's something called background extinction, and the background extinction rate is important to note that it's not, there's always things going extinct. It's the rate of extinction that is crucial. And just like climate change, the climate changes. Temperatures go up and down globally, but the rate of change is often the most significant thing to consider. And the rate of climate change right now is precipitous. It's moving upward at a rate that is very much very unusual for the last certainly for the last 10,000 years, but really for the last 800,000 years or so. But here, background extinction are just the extinctions that are going on all the time as part of a natural course of evolutionary processes. There are events, though, we call mass extinctions, where large numbers of families die off. And those are well above the background extinction rates. But typically what happens with extinction is you have a pre-extinction ecosystems and pre-extinction fauna. Some event occurs, or a series of events, or whatever, and they could be a long period of series of events. They could be a short, sudden event. The extinction occurs, biodiversity loss ensues, and then, of course, through that, new niches open up, and recovery occurs over time. It's a slow process, but it occurs over time. And you, of course, get new evolutionary development during this process. And then you have the post-extinction fauna. In terms of a sixth extinction, the one occurring today, which is occurring, we're right in the midst of the extinction. The recovery and the post-extinction are way down the road right now. But this is how extinction works generally. So there's the background extinction. Then there are these pulses of major events that occur. And these events occur because of outside influences, typically. And I'm going to focus in on the Ordovician, because that's one that I think is one of the least, as far as causes, least pinpointed as to what led to it. But we have a pretty good idea at this point. Here's another way of looking at it. This is the famous Sepkoski, Mark Sepkoski curve. This goes back a while now, but looking at number of families in the ecosystem. The Paleozoic, of course, had a pretty consistent number of families that existed pre-Pangea. Pangea forms, and there's major biodiversity loss at the end Permian extinction. And then biodiversity increases significantly during the Cretaceous. Paleozoic fauna are mostly marine organisms, and they're still around. We still have lots of their ancestors. They're all the shellfish and everything else. But the modern fauna are reptiles and mammals and things of that nature. So they've really increased significantly. But again, it looks like we're still at a biodiversity high. And of course, this is all geologic time. So remember that is the case. Anyway, the Ordovician extinction occurred right at the boundary, or right near the boundary between the Ordovician and the Silurian periods. We call it the end Ordovician, or the Hernanchian extinction sometimes, named after the stage of the Ordovician in which it occurred. And we see, here's some key groups that were really dominant at the time, and we can see that they go through bottlenecks. So you have an extinction period where you have significant loss of biodiversity, and then it eventually recovers towards the very end and into the Silurian period for most of these groups. But what's happening at the time, we use proxy records that tell us something about the situation of seawater. Here we have oxygen 16, 18 isotopes, and oxygen 12, 13, or carbon 12 and 13 ratios that we pull out of ocean sediments largely, and other sources. But these ratios, and when they're high, indicate a glacial period, or a colder period globally, because of the way the isotopes 16 and 18 here and 12 and 13 here, the way they fractionate in the atmosphere during this time. So you can spend a little time looking into isotopic fractionation, but these ratios are very commonly used proxy measures. We pull them out of ice cores as well, use them for more recent climate change data as well. So of course, these are the result of other things going on. So what could be going on that would lead to a glaciation, a major global glaciation during the end of the Ordovician, that would cause increases in the isotopic ratios of carbon and oxygen? That's a good question. Typically, what causes cooling could be sulfur dioxide particles in the atmosphere from volcanism, changes in Milankovitch cyclicity, and so forth. It turns out that at the end of the Ordovician, we have evidence for a number of things going on. Here again is your pre-extinction fauna, your survival recovery fauna, the survival fauna, and so forth. This is going back to the extinction curves from several slides ago. When we look at the isotopic ratios, they're high for oxygen and carbon during that time, indicating some sort of glacial action happening. What's also high, or actually declining during the Upper Ordovician during the same period of time, is the strontium 7786 ratio, or I'm sorry, 8786. Oop, that's a typo. That's strontium 8786, which is an indicator of continental erosion or erosion of rocks. So so we mentioned in the last lab video that when you have increased erosion, you can actually pull CO2 out of the atmosphere and cool things. But here we have a decline of erosion. Strontium 87-86 ratio is an indicated decline in erosion. But at the same time, we have a cooling going on. So that seems to actually go along pretty well. Decreasing ratios are also indicative of high rates of hydrothermal exchange of seawater with hot basalts at major spreading centers, as well as volcanic activity in general. So now we're starting to see here lots of volcanism going on. We don't know whether it's what we call large igneous provinces like the Deccan traps in India or the Siberian traps or Columbia River flood basalts, which are really, really large amounts of eruptive material coming out on land. But during this time, Rodinia has broken up and we're on our way to Pangaea, but we have a lot of rifting going on in the oceans at this time in spreading centers. Lots of volcanism at spreading centers, which could be related with what's causing the decline in strontium ratios. So all this volcanism, of course, is also going to be spewing. That's so much the volcanism at ridge centers, but that is an indicator that something's going on in terms of volcanism. But how do you get ash falls and so forth? Well, it turns out that in China, South China, there's evidence now for a large igneous province that may have been erupting at the time as well. So you not only have spreading center volcanism, you may have continental volcanism. Of course, China was just a small continent off by itself at that time. It wasn't the modern country you think of. There's also in these rocks spikes in mercury, which would indicate a volcanic origin of that mercury. And so here now we have ashfall deposits all over the place, large volcanic ashfall deposits. We have decreases in strontium ratios, indicating lots of spreading center volcanism, and we have high mercury spikes. So there's a lot of really good evidence for this. I'm going to leave it at that because some of you might pick that particular extinction, but I don't want to belabor it too much. The other four have very interesting data to go with them as well, and the Ordovician has more to it than just that bit of the story. But as you choose an extinction to study, that's the kind of stuff you should be looking for: graphs and charts, and to make an argument for your point. So the sixth extinction, again, sometimes referred to as a result of the Anthropocene. Again, the Anthropocene is right now this informal designation we use to describe we think is probably it could be the last couple hundred years, could be the last 10,000 years, the whole Holocene, or it could just be since 1960 or so. We haven't decided if it's going to be a real period, a real epoch or not, on the geologic timescale, or when it would begin and all that. That's all a point of interesting discussion right now amongst academics. But we do know that humans have created, as a force of nature, new realities for the planet. It's the only single species to have ever done that we know of. So overexploitation of species, agricultural activity, all these things are contributors, are causes to changes in the atmosphere and the geosphere and the hydrosphere and the biosphere that lead to major extinctions. And so some interesting couple places you can go to look more into this. Aaron Ellis at University of Maryland is really into ecosystem change study, and has come up with this term anthromes, which are kind of like biomes, but they're human biomes. He calls them anthromes. And so here's the changes in anthromes globally from 1700 to today. And you can see just looking at the color. One just says look at the color and see the major changes from 1700 to 2000, over 300 years. I mean, just looking at rice villages and so forth in India and China, and of course the effects that rice planting, or rice agriculture has on the atmosphere and on the biosphere and hydrosphere is very significant. Look at North America, of course. North America in 1700 was very, very sparsely settled by Europeans, a lot of indigenous populations. But look at the changes since then, and it's quite significant, especially with rangelands, things that were once forest and are now rangelands in places like Brazil and of course the U.S. Um, Very significant changes. So that's one place you can look at some of Ellis's work at University of Maryland. It's very interesting. Also, the Stockholm Resilience Center has created this interesting planetary boundaries uh, image that they update regularly. And what it's looking at are boundaries for the entire ecosystem, but it's a whole bunch of different things. Biospheric integrity is what you're focused on with the extinction, but they're looking at climate change and other. These are sort of the basket of unknowns: ozone depletion, aerosol loading, acidification, biogeochemical flows, that's carbon cycles, phosphorus, nitrogen, and so forth, and land use system change. This red line, and of course, qualitatively right now, but quantitatively it has a value as well. But it's considered a threshold, beyond which we don't know what happens. And you can see one of the things that's at a threshold right now, or beyond that threshold, is genetic diversity. Genetic diversity loss is very significant right now. We probably have a little bit more. There is a little bit more room for climate change. That's probably going to change over the next 100 years very precipitously. But other areas we're coming very close to having big problems. This right here is going to lead to big problems down the road here, because a lot of these biogeochemical cycles, uh, that put CO2 in the atmosphere, which has a residence time in the atmosphere of up to thousands of years, hundreds to thousands of years. So when you put CO2 in the atmosphere, it stays there for a long time, and we aren't necessarily feeling all the effects of climate change that are to come yet from human activity. So that's why that's there and not further out. But this has an effect on this and on this, and so forth. So anyway, there's a lot more there. If you look up the Stockholm Resilience Center, you can find a lot more information on these places. So anyway, again, choose an extinction event. Be thinking about it in the context of the Anthropocene sixth extinction, and see what you come up with. But make sure you support your final project with data. Make sure you're providing charts and graphs from as scholarly the more scholarly the literature, the more peer reviewed the literature, the better. So until then, it's been a pleasure working with you. And if you have more questions, again, ask your master teachers.